after the Happy Independence Day and Happy Higgs Day, then this is number 1 still, but number 2 becomes H. Number 3 is now Z, number 4 is W, number 5 is B. We would like to know when the Higgs meets the top, what interesting things might happen. We would like to learn some information. And I'm going to briefly mention the motivation and introduction. Then I'm going to show you a general type 3 2-Higgs doublet models, followed by a special case study for Higgs decay into BB bar in TT bar decay. One at the top will decay into a Chung and a Higgs. The Higgs will decay into BB bar. Then we are going to study if the Higgs can decay into ZZ star. Then what information can we learn about the TCH coupling? And I guess I will exhaust my time before time is up. So there is a bonus about a special 2-Higgs doublet model for the top quark. And I hope some of you will ask me questions. So I get to explain this 2-Higgs doublet model. And on this page, I want you to pay attention to the highlighted term. That is, our highlighted factors. That is rho CT times cosine beta minus alpha in the type 2 language. We learned something very interesting from Babar. And Babar published their paper. Then a group of physicists, followed by another group, discussed what we might have learned from the Babar anomaly. Babar defined R star means the ratio for D star. Without star means for the D. D star means excited state. So they define 2 ratios of R for tau nu versus lepton nu. And from these 2 ratios, they said, if we assume 2-Higgs doublet models of type 2, then tangent beta of a charge Higgs should be 0.44. However, for the other one, it will be 0.75. So this first number is for R of D, the second number is for R of D star. These 2 numbers are incompatible if we hold on to type 2 of Yukawa interactions that is adopted by MSSM. That is, down type quarks and leptons will couple to phi 1, up type quarks and neutrinos will couple to phi 2. And Babar explained that they have excluded type 2 2-Higgs doublet models with a 99.8% confidence level. Another information we learned is these 2 numbers are not compatible with B to tau nu. Therefore, this could be something beyond the standard model and even beyond type 2 of 2-Higgs doublet models. And here is a Lagrangian we learned from this paper. And I understand everyone has his favorite notations for Lagrangian, and we'll follow this paper. The kappa terms are the diagonal terms in the original interaction eigenstates. And the rho terms has both off-diagonal terms and diagonal terms. And then later, we rotate phi 1 and phi 2 components into mass eigenstates for light scalar and heavy scalar and a pseudoscalar plus charged Higgs particles. Now, sine beta, S sub beta minus alpha means sine beta minus alpha, and C sub beta minus alpha means cosine beta minus alpha. For students and postdocs, since the standard model is so wonderful, most people now expect there is a coupling limit of two Higgs doublet models. In that limit, sine beta minus alpha will approach 1, cosine beta minus alpha will approach 0. So this scalar will decouple from WW and ZZ. Therefore, in the decoupling limit, we are going to have one light scalar, probably with the mass of 126 GeV, and it will behave exactly the same as the standard model Higgs. Now, if we want to explain Babar anomaly, we need the rho vector, rho CT, to be about 1. Let me remind you what the rho is. So in this equation, this rho can be, let's say, just for fun, rho UU, rho CC, rho TT, rho UC, rho UT, etc. And for the uptype, we can have rho CC, rho CT. So rho CT is this term that will generate flavor change in neutral Higgs interactions. And if we want to explain the Babar anomaly, we need rho CT to be about 1. But I also told you, cosine beta minus alpha should be not too large if we want to explain the standard model Higgs. And we have learned that today, several speakers and yesterday's speakers showed you this wonderful figure made by CMS. Most Higgs channels are approaching the standard model value. So that means rho tau tau and rho BB should be tiny, because Higgs decaying into BB bar and Higgs decaying into tau tau are the same as standard model expectations. Experimentally, I think I should also think about D. When we were working on these two projects, Bao Di was our advisor and our cheerleader. He kept saying, go for it, go for it. And this is what we might do. So we learned a lot about CMS from Bao Di. And so, rho BB, rho tau tau should be tiny. However, we don't know much about rho CC. Just for fun, to challenge Echo and Bao Di. Someday, can you tell us what the branch ratio of Higgs to CC bar is? This is for fun. You don't have to answer. But if we couldn't answer, then it will be fun. So we don't quite know. And rho TT, let's assume it's not quite constrained. This second paper written by this group, they suggested rho CC should be less than 0.2 to be consistent with ds to tau mu and the ds to mu nu. So we now have two parameters we don't quite know, and the one that could be large would be rho TT. And in the near future, if we understand the production rate of Higgs, maybe we'll understand rho TT better. So now this is a brief review for experts as well as students and postdocs. The most important channel for the discovered scalar is BB bar, about 60%, followed by WW star, about 22%. Then you may be surprised. Number 3 is glue. Higgs decaying into glue has the branch ratio of almost 8%. Then followed by tau tau, about 6%, and then ZZ star. ZZ star, at first we thought, well, it has a small branch ratio. But we learned from our experimental colleagues, this is the gold channel. This is the golden channel, not just gold-plated. Gold-plated, because we understand leptons better than photons experimentally. And then followed by CC bar and gamma Discovery Channel, but now this star might become more important to understand the property of Higgs. Let me remind you, in the decoupling limit, almost 1, gamma gamma will be dominated by W loop, and we learned from V to S gamma, charge Higgs should have a mass above about 600 GeV. And tau tau, we can see some information soon. And CC bar, we may not know until many, many years later. And TT bar, we are still waiting to understand the Higgs TT bar coupling. So now, I want to briefly mention a cute model. If top is the only, if top is so much more massive than all other fermions, is it possible top is the only fermion that will couple to a doublet we call phi 2, while all other fermions will couple to a doublet we call phi 1. In this model, tangent beta V2 over V1 is chosen to be large, and such that lambda t and lambda b are comparable, but because of V2 much larger than V1, MT is much larger than MB. And there are flavor-changing neutral Higgs interactions in this model, and there are secret violation in this model. Thank you. Does this sound better? Yeah. Thank you. Okay, now this is how we assign Yukawa interactions. Top is the only one, has bilinear coupling with phi 2. All other fermions will only couple to phi 1. Of course, W and Z will couple to both, such that we have V1 squared plus V2 squared equals V squared. So to be continued, if you are curious, ask me questions when my time is up. Okay, now let's use an effective Lagrangian and describe the scalar T bar C coupling in terms of lambda Tc and A naught T bar C coupling as lambda Tc. Let's assume they are the same. Of course, this can be prime and this can be different. And in our general language, lambda Tc should be lambda T. Lambda Tc should be the same as lambda Ct. We assume that this is emission, and it is rho Ct times cosine beta minus alpha. Rho Ct needs to be 1, and this has to be less than 0.2. Therefore, we expect if lambda Tc is 0.2, then the branch ratio of T into Ch will be about 1%. This was suggested by Zheng Dapei and Mark Scher. This is the geometric mean of MT and MC, such that when you have TT bar coupling, this recovers the usual top Yukawa coupling, and the same for the Chung. In general, we are going to take it as a free parameter. And this was calculated by George in 1991 for both scalar and for pseudoscalar. Plus sign is for scalar and minus sign is for pseudoscalar. And we take the total width to be T into BW and T into C and a scalar, or a pseudoscalar. This is for case study. If we take the Cheng and Scher ansatz, then lambda Tc is about 0.063. So the allowed number from the prevalent group is about 0.2. So we have a room of a factor of 3. Now, if lambda Tc is 0.063, then this branch ratio for 120 GeV Higgs will be about 3 times 10 to the negative 3. And it becomes smaller as this mass becomes larger. So for 126, this is about 3. So it's 0.3%. My postdoc Josh he put in flavor changing neutral Higgs interactions into math graph. So we calculated our background and signal with math graph. And I want to remind you, for a scalar, you have the BB bar followed by WW and then tau tau and so on and so forth. I did not put in glue glue. Actually, glue glue should be slightly higher than tau tau. Should be somewhere right here. If you have a pseudoscalar, however, there would be no WW, no ZZ. So the most important channel will be BB bar. I think tau tau will be about 8%, and glue glue will be still the same, about 7%. Okay? So I just told you we use math graph, but I want to remind you, behind the glory of math graph, there is something called Hellas. Hellas was written by three wonderful physicists, Murayama, Watanabe, and Hagiwara. They give us a wonderful tool to calculate all the Higgs interactions numerically. We have two B's from Higgs decay. We have another B from a top. So we have three B's. And we number our B's according to their PT, B1, B2, and B3. This jet for our signal is a charm. For our background would be a strange quark. And you can tell if the Higgs mass is large, this charm would lose energy. Therefore, we cannot go very far in MA or in MH because this charm will be removed by acceptance cuts. So this is a table to show you the branch ratio times the cross section. So if we have a signal for MA equal to 120, it's about 44 femtobarn. If we have 20 inverse femtobarn, it will be about 800 events before cuts. And let me remind you again, the branch ratio for T to CH is about 0.3%. And for Higgs to BB bar, it's about 70% for a pseudoscalar. It's about 60% for a scalar. Okay, this is the background, and we have additional backgrounds. We spent about 4 months to check this background. And the TT bar background, the dominant background, we finished it in 1 week. So sometimes you spend a lot of time to do consistency check with the contribution that is about 5%. Okay? So we require mass reconstruction, and we require MBB jet to give us MT, MB lepton nu to give us MT, MBB bar to give us MH, and MB jet to give us MW. And we'll veto MW. And we learned from Tao Han and his collaborators, there is a wonderful additional kinematic choice to choose the flavor changing neutral Higgs signal. That is the energy of the charm quark in the rest frame of the top quark. So now let me show you at 8 TeV, if we choose 20 inverse femtobarn, then let me show you the signal. So the signal, let me see. I think, okay. Okay. Dark blue is a scalar, as psi n is pseudoscalar. So big H is a scalar, A is a pseudoscalar. Then you can see the 3 sigma limit in magenta. You can see the 5 sigma in green for 20 inverse femtobarn. Okay, and this is for 14 TeV. For 14 TeV, everything becomes easy. Now, this is a contour of lambda Tc versus the branch ratio of Higgs to BB bar. For 8 TeV, thank you. And right here. Thank you. So for 8 TeV, this is probably where we are. So before long, we are going to find out from Baodi and his collaborators, his students and postdocs, whether we can discover FCNH interactions or we can learn some important information about this lambda. At 14 TeV, you can tell that the discovery region can be extended further down. So even with a small lambda Tc, with a small branching ratio of Higgs to BB bar, this can be promising. So I lost my remote control. I can use the key. Okay. So now here is a very interesting analysis with CMS data. With 7 TeV and 8 TeV data, there are 13, 8, and 4 events with 4 leptons. 4, 0 jets, 1 jet, and 2 jets. If M4 lepton is between 121 and 131. And from this analysis, because TT bar will give us additional jets, so we can place a very informative constraint, that is the branch ratio of T to CH should be below 1.5%. I understand that Yura and his collaborators have done similar analysis to place constraints on lambda Tc and branch ratio. And this is what we found. Okay, so let me conclude, and I hope some of you will ask me about the special Higgs-Doublet model. Okay, I hope you agree. We have 2 most massive particles, the top quark and the Higgs. The Higgs is the mass giver. The top is the most massive particle, and we hope to learn something important. If we can find FCNH interactions, this would be beyond type 2 of Higgs-Doublet models and MSSM. So we have done BB bar, and we did a quick estimate for ZZ star. And we are currently doing WW star and tau tau. We would like to know if we can increase the discovery potential for flavor-changing neutral Higgs interactions. And we might be able to kill 2 birds. The first bird is electroweak symmetry breaking, and another is 3-level flavor-changing neutral current in LHC experiments. Thank you.
Any question except the spatial Higgs model?
What you have the title on the paper? What you need how to chair of do the chairman work? I mean, Coach Wishu is also leading the CMS.
There is some historical reason. Baodi is doing all the hard work.
You mean Kaifeng is not doing
Kaifeng is, but for different channel. For Higgs to BB bar, I think Baodi is the leader for the experiment. Am I right?
Well, yeah, I just use my mouse. The students do.
So I would like to understand what the numbers are. So the lambda Tc bound for the light Higgs, so the bound on the lambda Tc is about 0.2 from this H to, so T to Hc. It's about 0.2. So what does that translate into the coupling to the Pseudoscalar and the heavy Higgs?
Okay.
It's there's some dependence on tangent beta.
The thinking. So let's talk about lambda Tc. The branch ratio is about 1.5%. Therefore, lambda Tc, if we calculate, is about 0.3. The allowed number. So lambda Tc at this moment is less than about 0.3.
That's right.
Okay. We did not pay attention to tangent beta yet. Of course, we can write it as rho Tc. So rho Tc is about 1. Cosine beta minus alpha is about 0.2. So this simple argument 0.2 will give us about 1.1 or 1.2%. That's stronger than this. So we have a theoretical, we have an indirect information that gives us about lambda Tc, that is 0.2, and we have a direct estimate from ZZ star that gives us lambda Tc about 0.3. So there are two different channels.
Yes. Maybe I didn't quite follow. So when I go from lambda Tc to your rho parameter,
Lambda Tc equals to rho Tc times cosine beta minus alpha.
not sine beta.
No. Okay, let me go back and show you.
Okay. That's okay.
Oh, sorry. Right here. So this is rho Tc is lambda Tc is rho Tc times cosine beta minus alpha.
Yeah, so it doesn't need
Okay.
That's it.
Okay, other questions?